I don't know much about quantum. I just learned about quantum probably a few months ago from Tong Yang and Xiaodi. But I realized that I work in machine learning. I work with tensors, but I realized a lot of this tensor algebra seems to be very related to quantum stuff. But today I'm going to talk about a class of problem that is pretty popular in machine learning. And at the end of the talk, I'll very briefly tell you a success application of using quantum algorithms to speed up classical machine learning algorithms, basically inspired from, oh, I forgot, sorry. Yeah. Okay, does that work? Okay, perfect. All right, so the title, as you can see, is Discover Latent Factors in High-Dimensional Data Using Spectral Methods. I guess I don't need to motivate much about success of machine learning, especially, supervised learning where you have deep compositions of nonlinear functions and you have very powerful computation power. As long as you have enormous labeled data, you're able to do very successful machine learning. Yeah, you're able to do very successful machine learning. I guess here, using neural nets, right? However, we are more interested in a class of more difficult problem, which is a lot of you are very familiar with unsupervised learning. Say you wanted to learn filter bank, you wanted to do feature extraction, you wanted to do extract embeddings from, say, documents, you wanted to find topics in those documents. Well, you don't have any label data to start with, right? So, oh, okay. You don't have any label data to start with, therefore it is called unsupervised learning. It's mainly summarizing key features in data. We know humans are very good at doing that because we accumulate general knowledge or common sense, but machines are not necessarily good at doing that. So in this talk, we'll be mostly interested in interpretable modeling or learning of the data. So it's not going to be neural network, but we're more interested in theoretical guaranteed learning and extract features that are interpretable. All right, so here is one example of unsupervised learning with big data, but what are the challenges, right? So the curse of dimensionality, meaning like once you have more information, you have more unknowns, and therefore your model becomes more challenging. Actually, in a lot of cases, doing unsupervised learning is to do density estimation. So density estimation in high dimensional data becomes really, really hard due to the curse of dimensionality. But as long as you observe in a lot of scenarios, machine learning applications, there are some underlying representation that will make the entire presentation pretty simple, and therefore doing density estimation becomes tractable. For example, in these scenarios, you have limited number of cell types in terabytes of brain slices. In documents, you have only limited topics and only limited communities in social networks. However, finding those hidden structure becomes intractable as well as like finding a needle in a haystack in general. So I guess my slides are cropped somehow. Let me try to. How do I maybe just do? Okay, this will work. Yeah, this works. Okay, so I guess my solution is a unified tensor decomposition framework, and you'll see in a bit what I mean by that. Well, here are some applications that I just wanted to very quickly go through. Using this tensor decomposition, you do document modeling, so you can observe words in documents without considering order, but you can find topics which are mixed sometimes. And now in social networks, you observe network social ties, friendship, but you want to find hidden groups of social actors. This will be very relevant in recommendation systems and so on. So here are some results. I don't want to go into the detail, but the takeaway message is doing these kind of spectral methods and tensor decomposition, you not only get accurate result, but you can also be much faster, right, compared to state-of-the-art variational inference, which is a likelihood-based method doing like optimization over a non-convex lower bound of a likelihood. Okay, so another application was like doing, tensor decomposition to find neuronal cell types in the brain, which is also a very challenging task. I don't want to go into the details. I wanted to just show you some few applications, word sequence embedding, finding, vector representations of sentences, or finding a disease hierarchy using, logged human patient healthcare data set and so on. All right, so all these kind of applications basically involve finding some hidden and compact structure that is embedded in high-dimensional complex observed space, which is basically doing density estimation. So how do we model these hidden effects? The kind of approach that people can think of a very basic one, mixture models or clusters. Not necessarily you need to put a probabilistic model, but maybe just a categorical hidden variable. That's not observed, right? Although I'm colored, these nodes are colored here, but I don't necessarily observe them. Or you can think about a more advanced approach, which is probabilistic models where you have these hidden variables. They could even be hierarchical. They could themselves have some hierarchical structure. Here, these edges actually are a very conventional representation in graphical model, which means that if you remove something, then two parts become disjoint, then that means it's conditional independence. Okay, so today, this talk, I'm going to talk some basic mixture model and some advanced models, such as topic models, how you do that using tensor decomposition. Well, so before we do that, right, so the basic goal is, again, as I mentioned, you can use this flow graph to basically understand what I'm going to do. You have unlabeled data, right? So in machine learning algorithms, you put a model on top of these data. In this case, it's latent variable model. And you find some learning algorithm, and in the end, you want it to do inference, right? So, so what are the challenges? First, the conditions for identifiability. Can these models actually be identified if you have infinite amount of computation and data, right? So that's the first identifiability problem. And the second problem, are there tractable algorithms under these identifiability? Right, so here we're going to tell you, under a wide class of model, actually there are identifiability, and you can also use finite number of algorithms to get high probability results. And we can provide those algorithms later on. All right, so another challenge is like the efficiency. Right? So can you efficiently learn the latent variables? Say, that if you use some of your familiar with Monte Carlo, MCMC, so basically it's a random sampling, but it requires exponential mixing time. It could be really slow, and therefore it's not necessarily efficient. We don't characterize as efficient algorithm because we care about polynomial time algorithm in terms of dimension, because we are in the high dimensional regime. Right? So the likelihood method, like I said, variational inference, the likelihood in general is non-convex, therefore it's not scalable at all. And you could imagine if you have exponential many local optima or critical points, you might have a problem converging to the good answer. So, so in this talk, we care about computational and sample complexity. Right, so indeed, the claim here is that we can find an algorithm which is basically a tensor decomposition that is guaranteed and efficient learning through spectral methods, which is again tensor decomposition. So here are some contributions that I guess we can talk about a little bit, like guaranteed online algorithm with global convergence guarantee. So overall, this algorithm is going to be online. It is very scalable, and there is a global convergence guarantee, although it's a non-convex optimization problem. Yeah.
Maybe just as a very basic question.
Right.
I got a little bit lost. Do I understand the first arrow to mean is the process of, let's say, finding the best probabilistic model compatible with the data I see?
Not necessarily best, but under some hypothesis set.
Okay.
Right.
What's the second arrow? how do I go from the inferred model to whatever
Right. So
box there is?
this is just a model with an unknown parameter. Let's say, mixture of Gaussian, then you don't know the mean and the covariance for those mixture, for those components. So using these methods, your learning algorithm wanted to infer the parameters of these model.
I see.
Yeah, and then at the end, once you have the parameters of the model for new data, you wanted to do prediction. Yeah.
Do you assume that the decomposition, the number of terms is very small compared to the problem?
Yeah, it is a
Low rank?
it is a low rank structure. Well, you can extend it to high rank, but there will be some other discussions, which is like incoherence and something like that, which I'm not going to talk about in this talk. All right, so some, contributions, highly scalable, parallel, dimensionality reduction, and things like that. And we have a library. If you're interested, please feel free to try it. As I said before, there are interdisciplinary applications and can be invariant, extended to models with more invariance. But again, I'm not going to talk too much about this. Well, so let's see. First of all, I'd like to introduce a very, very old method, which is method of moments. So what is method of moments? It has actually been there for a long time. I believe more than 100 years or so, right? So actually, we can think about this method as three steps. One is to determine function of model parameter theta estimatable from observed data. So in that case, right, so this is your theta is like the class of hypothesis your algorithm is trying to learn, which is basically the class of latent variable model you put on your data, right? So f is some function that you need to specify, which is the main challenge in designing these algorithms using method of moments. We'll see, first, using that model, you would be able to derive analytically the expectation, of some f of the data under this model theta, which is going to be a function of theta, right? As long as you identify what the f is. And now the second step is you form some estimates of the moment using data. Well, assuming that data is IID, then this empirical estimation of that function just becomes something that you can estimate using this IID data, assuming that you have n such samples. And now in the end, you do moment matching, which is basically to say when n is really large, these two terms should be equal. Well, when n is large enough, in high probability, these two things will be also equal. So therefore, you can imagine that a high probability bound could be achieved using that approach. So, well, although this method of moments seems to be very simple, because it's basically moment matching using the population moment with the empirical moment, then the idea here is, the challenge is, how do you find such f for this specific class of function, characterized by theta? This is a toy example. For example, you wanted to estimate Gaussian variables. How do you use method of moments to do that? Just let's say you are given n such IID samples, then how do you do Gaussian estimation? Basically, your f becomes very simple. Is either mean or covariance, because Gaussian is completely characterized by mean and covariance. So as long as you can match those two moments, you're fine. Okay? So, well, I guess I don't need to talk about what's a tensor in this audience. Well, still, let's say tensor is a multidimensional array. It is a higher order matrix, and in fact, we might have different notations. I call this tensor as a third order tensor, so that the number of modes is, the order here. And, you have tensor slices. In this case, as a third order tensor, of course, I cannot draw fourth order or higher order tensors. Well, so we define a tensor product, which I guess you're all familiar with, but I guess the notation might be a little bit different. Here, I have vectors A and B, and I define the tensor product of A tensor B, which becomes a rank 1 matrix. And each entry, let's say I1, I2 entry becomes I1's entry times I2's entry of these two vectors. Okay? And now, similarly, you define a tensor product over 3 vectors becomes a rank 1 tensor, third order tensor. And the entry becomes I1, I2, I3's entry becomes I1's entry times I2's entry times I3's entry. Okay? So pictorially, I'm going to use this to denote tensor products. I guess the notation is a little bit different, although the ideas are very similar. So tensor in method moments, what do I mean by tensor in method moments? First, as I said before, the F is the main challenging quantity that you need to define. So in this case, let's say pairwise relationship. That's one way of how you define F. What do I mean by that? Let's say you have signal or data observed from the RD space. Well, so I guess in my community, we mostly work with real numbers, but you could somehow extend it to complex numbers, I guess. I don't know how difficult it will be. And then rank 1 matrix becomes, the ij's entry of the rank 1 matrix becomes the tensor product of x and x. So the signal, tensor signal. And now this is then the pairwise relationship. But if you consider aggregated pairwise relationship, which are, in this case, let's say population aggregated, which is then becomes the expectation of the x tensor x, it becomes the M2 matrix. In this case, my f of x becomes x tensor x. Okay? So now if you consider higher order relationship, which is say triple-wise relationship, then again you have data from RD. Then you can consider rank 1 tensor, which is like defined as the x tensor x tensor x. Similar definition, I don't need to repeat that. Then the aggregated triple-wise relationship becomes expectation of x tensor x tensor x. So this is another way of defining F. And we'll see in a lot of cases, F, well, the complexity of how much complexity you need in F in order to, completely characterize the density function becomes a little bit challenging. So people will say, can I use a matrix or covariance matrix, or do I need to go to third order relationship or triple-wise relationship, or do I even need to go to higher order relationship? In this case, we're going to show actually a wide class of functions don't need to go to higher order relationships. You only need very low orders to do moment matching, and you can completely characterize the density function, which is so-called identifiability. But before that, let's say we wanted to introduce one concept, which is called CP decomposition. So let's say you have a tensor. If it is rank R, then the tensor can be approximated using summation of R terms, and each term is just a rank 1 tensor. Any questions? All right. So here is an idea of why tensors are powerful. It seems like tensors can only be thought of, at least in the real space. A lot of people think tensors are just higher order matrices. Why are they powerful at all? Let's think about a motivating example. It's basically a toy example. Let's say you wanted to do matrix orthogonal decomposition. It is not going to be unique if you don't have an eigenvalue gap. Here is this example. Let's say you have just identity, which is the simplest matrix you could think of. If you wanted to do decomposition, you find out that it either can be decomposed into E1, E1 transpose plus E2, E2 transpose, which are these basis vectors here, or it can be also be decomposed into U1, U1 transpose plus U2, U2 transpose, which are just rotations of those basis vectors. In fact, any rotation of these basis vectors can be eigenvectors of these matrix. Okay? So it is unique, however, with eigenvalue gap, right? Because we're thinking about a matrix orthogonal decomposition, therefore it is unique when you have an eigenvalue gap. So what happens in tensor? Let's say you have a tensor. You start with a tensor. The tensor does have an orthogonal decomposition, although in a lot of cases, the existence of such orthogonal decomposition is not necessarily there. But let's assume that you do have a tensor. It does have an orthogonal decomposition. And let's say your tensor is U1, tensor U1 plus U2, tensor U2, tensor U2. You can say in this case, your eigenvalues are equal, so there's no eigenvalue gap, right? So, however, so let's assume U1 is orthogonal to U2 as well. So, however, if you consider doing like slices of the tensor, so that direction, it becomes matrices. And one interesting property you find from those matrices are, they're simultaneously diagonalizable, meaning like their eigenvectors are going to be equal, U1, U1, and U2, U2. Although the eigenvalues now becomes different because you have to, find a slicing, find a linear combination of these slicings. Therefore, the entries of this U1i, U2i are not necessarily equal. Yeah.
Why do the slices have to commute? Why do the slices have to commute? I missed something.
Oh, I don't think they commute. What do you mean?
They're simultaneously diagonalizable.
Yeah. Yeah. Well, so just by very simple linear algebra, you can see slice I becomes U1i, so i's entry of this vector.
What was the statement? For every three-rank tensor, these things commute, or because this cannot be?
For an orthogonal tensor, if you find the slice, right? So for a tensor with an orthogonal decomposition, any slice share the same eigenvectors. Yeah. From the same dimension, of course, right? So if you are, you don't trust this result because you could think about cases where U1i is equal to U2i in some cases, but then if you do a random sampling from a unit sphere, let's say you find some coefficient Ci, and then you do a linear combination of these slices, then with high probability, you will get these eigenvalues not equal to each other. So this is just a very motivating example, toy example, saying tensors can be powerful, right? For example, you don't need eigenvalue gap in order to have a unique orthogonal decomposition, and that's because you have an extra dimension of information that will help you in identifying your model. Okay, so now I'm going to use an example. How much time?
So you have until, you calculate 25 more minutes.
Okay. Well, so I'm going to very quickly go through an LDA model and a community model using method moments. I'm going to walk you through how you can use method moments to estimate a more complicated cluster model. And in fact, in the end, we're going to very briefly talk about there is a guaranteed online algorithm for doing tensor decomposition. And at the end of the talk, we're going to talk very briefly about a recent joint work with Xiaodi and Tongyang on quantum algorithms to finding leading eigenvectors computation for matrices. Okay. So let's get started. So can you tell me how many of you have heard about latent Dirichlet allocation? Okay, maybe we can just go through it very quickly. So, topic model, usually people try to extract topics from documents. And in a lot of scenarios, people just don't want to consider order. Therefore, there is this bag of words model basically says that I only look at the counts of the words in the documents, and I wanted to use that very simple statistic to infer the topics in the documents. So this is basically to learn a hidden process that drives the observations you get. So what is this generative model that basically lying underneath this process? So you basically have a topic proportion, which is in a lot of cases people use Dirichlet for a document. So here this is a document, and you have a topic proportion, which is one sample from a Dirichlet distribution. And in here, let's say you have 3 topics, and this is the sample that you sample from the Dirichlet. And now, once you draw the topic, then you wanted to specify what is the generative process that you generate words from the topic. So here, a word is then a token. How do you do that? For each word, you first decide what topic should I talk about. In this case, let's say this one, I decided to talk about the yellow topic. Then I try to decide under some conditional probability, or in this case, crime topic, what are the probability that I'm going to draw these words from my dictionary book? Let's say I have a dictionary, I look at my conditional probability of those under this specific hidden variable topic equals to crime. So these are unknown. These are my model parameters. Your goal is then to find these model parameters by looking at the documents. Is that clear? Okay. Right, so basically, mathematically, what this is saying is I wanted to find these conditional probabilities of my observed word, given that my topic is J, right? So the difficulty is that the topic is really hidden, and therefore it is very challenging.
Just as for this, you could do in a supervised way in principle, right? You could feed the database with papers and topics, and then
You can't, well, if you have labeled data, yes, but in a lot of cases, you don't have labeled data. Well, so here is how moment matching work in this case. So the overall thing is just latent dirichlet allocation, right? So it is again just a class of distribution that you wanted to do density estimation over. So ideally, you can use moment matching. Then the idea is how do you want to design the f function in your moment matching, right? So here, in fact, we do wanted to assume some very weak assumption, which is linear independence over topic word tables. So this is the model parameters you need to estimate. And these columns are actually linearly independent. So here is one way you can design the F model. Let's say you only care about the occurrence frequency of words. What I mean by that is then you look at the expectation of the words, like how many times they occur in the document, and then you average over all documents. Okay, so this is the population, but you could imagine that you can find the empirical estimation of that. But so let's say here is an empirical estimation of that F function. Of course, you know that this empirical estimation is going to be decomposed into the linear combination of the columns of your topic word matrix, which is the parameter that you need to estimate. Any question? Okay. Which is the parameter that you need to estimate. Somehow, the problem is that you cannot find a unique decomposition for a vector, because you could find another decomposition, which is again, the same as the, empirical estimation of this occurrence frequency of the words. However, it's not unique. You could find another linear combination, which are not necessarily the models here. Then you consider maybe let's think about higher order moments. Maybe let's say co-occurrence frequency for word pairs. So in that case, that's, if you do an empirical estimation of this population quantity, in this case here, let's say this is the empirical estimation of the matrix, then by very simple linear algebra, that this becomes this decomposition where each of this component is a rank 1 tensor product of the components here. Now you wanted to ask this question: can I use this to uniquely identify my model? Basically, the first question of linear model identifiability. So the answer is, of course, no, because you don't have a unique decomposition for matrices as well, right? As we said before, even if it is orthogonal, not to mention that these columns are not necessarily orthogonal, they're only linearly independent, okay? So again, you cannot find that actual model, but what you can find is that you can find those subspaces under which your matrix is lying. So then you can find such a matrix. That matrix can actually orthogonalize the components. Therefore, if you find the co-occurrence frequency of word pairs, which is like the triple-wise relationship in the data, let's say you have an empirical estimation of the triple-wise relationship in the data, then if you do some kind of whitening, by doing multilinear operations on these modes of the tensor, using that W matrix, then the components actually becomes orthogonal to each other. So therefore, you know that orthogonal decomposition is unique for tensors. Therefore, you don't need to go to higher order, moments. So F can be only like a third order moment. Is that clear? Okay. So that's the basic idea. Unique orthogonal tensor decomposition. Because of the uniqueness, then the model is identifiable if you use moment matching using third order moments. So similar, you can think about estimating other density function as long as you can identify how many orders do you need in order to completely identify the model, then you're probably done using the method of moments to do the matching. Okay? So finally, you just project it back into the original space, and you can find the components of the model that you're interested in. So the takeaway message is that tensor decomposition uniquely discover the correct model, and you can learn topic models through very simple matrix and tensor decomposition. So the overall problem is basically reduced to a tensor decomposition problem, essentially a very specific class of tensor decomposition problem with orthogonal components, right? So I'm gonna skip this and tell you a little bit about a guaranteed online method for tensor decomposition. Because the overall, unsupervised machine learning has been reduced to do this tensor decomposition. Then the question is, can we actually uniquely identify the components of the tensor decomposition, right? So in fact, we find an online tensor decomposition method, which basically, it's assume you have a tensor with a 4-order tensor. In this case, because it's easier to show you why, it's a 4-order tensor, and then you have orthogonal decomposition. Then the objective is really to find an optimization objective such that doing an non-convex optimization becomes easy on that tensor, and to find the true components AI. Okay. So in fact, I don't want to spend too much time on this, but here we do find an objective function such that you minimize this multilinear operation of the tensor. So the first and second mode is the same vector, and the third and fourth mode actually is another vector. Those vectors are all so the norm of these vectors are 1, and the first and second and the third and fourth cannot be equal. So if under this very sophisticated designed objective function, then we can say that the objective function actually has a very nice property. Although it is non-convex, it has equivalent local optimal. By a very simple proof, you can show that it has equivalent local optimal. Therefore, you wanted to ask a very basic question: can SGD work under this case? So then you are left with saddle points. Then the problem reduces to: can you escape from saddle point? Yeah, using this method for tensor decomposition. So I don't know, maybe some of you know that we recently had a paper showing that for smooth second differentiable function where your Hessian is also Lipschitz, then we also assume that if you don't have degenerate saddle points, then doing an SVD actually converges to a local optimal in polynomial time. So it is not an exponential time algorithm, it's polynomial. It converges to a local optimal, but since for this tensor decomposition method, you find such an objective such that all the local optimal are equivalent, therefore it converges to the global optimal.
What if the AIs are not orthogonal?
AIs are not orthogonal,
Can you say anything?
then you can do whitening. So whitening, like the one I was showing, you find a W matrix, you do a multilinear operation on that tensor, and you find an orthogonal approximation of that tensor. Yeah. So orthogonality is actually very important here in order to show this very nice property of this tensor. Okay. So this is a global convergence guarantee for online tensor decomposition. So we're done. So basically, we complete the loop of solving an unsupervised density estimation problem using an online tensor decomposition problem with this very nice, objective function, which converges using stochastic gradient descent converge to the global optimum.
But why, how you know if there is no non-degenerate saddle points?
In this case, there is no non-degenerate saddle points, meaning for all your saddle point, your this is a minimization problem. Your smallest eigenvalue has to be smaller than some negative number. And you can prove that in this case.
Okay, well, I see.
Yeah. In general, you don't.
Right.
Well, so then some ideas, I guess I've already talked a little bit about it. Basically, the idea is that, saddle point has a zero gradient. How do you escape from saddle point? You just assume some non-degeneracy, which means like Hessian has both positive and negative eigenvalues, and then the negative eigenvalues become the direction of escape. However, unfortunately, you don't have access to Hessian for stochastic gradient descent. What you can do is, since you have noise, then you can prove that noise would actually help you to escape from the saddle point, although you don't exactly know the direction of the negative eigenvalue. Okay? So lastly, I wanted to spend maybe 5 minutes to talk a little bit about the recent work with Xiaodi and Tongyang on quantum algorithms for leading eigenvector computation. Like I said, I'm not a quantum person, so hopefully, I'm just showing you how a good application of quantum algorithms could help machine learning to speed up the convergence rate. So I guess we all know this PCA problem. Just to very briefly recap it, my goal is to understand how to do tensor decomposition or how to speed up tensor decomposition using quantum algorithms. But I guess this is a nice starting point to show that we can do that for PCA. Right? So we have samples, as I said before, is an RD space. Your question is then to identify the direction with the largest variance in the data. Right? So the problem formulation becomes very simple. You just wanted to solve this maximization problem where this U are in L2 norm 1. Right? So this is A is nothing but your covariance matrix. So the problem regime we're interested in is, again, the eigenvalues of the singular values of A is bounded from 1, it's semi-positive definite, and it's also bounded by identity. And it's also sparse, S-sparse. So meaning like each row, the non-zero elements of each row or column is smaller than or equal to S. So some classic algorithms, right? Of course, we're thinking about the regime where we do have a spectral gap. So meaning like the first leading singular value is greater than the second leading singular value. And if you order them in this way, then the corresponding eigenvectors are denoted as U1, UD. So our goal is to find this U1, okay, when there is a gap. So some method with Wormstadt. What do I mean by Wormstadt? Basically means the inner product of the two vectors. So this is the initialization, and this is your leading eigenvector. You wanted to make sure that that initialization do have some component on that direction. So it is non-zero. And then the iterative method actually can achieve epsilon precision after you do this many number of iterations. For power method, you actually need some order of SD over delta log 1 over 5 epsilon, such iterations. For Lantros, you can actually improve this to a square root of delta. Delta is the spectral gap. Right? So the basic idea is to replace the monomial AK by its Chebyshev polynomial approximation. So I'm not going to go into too much detail of this, but the question is then, although you can do this speed up in terms of the spectral gap, can you do speed up in terms of the dimension? Because we are in the high dimensional regime, right? So this linear factor in D is really not something we want. Hopefully we can get some log D, right? So this is actually motivated from, I guess, some quantum effects can achieve significant speed up. I guess you all know these examples, the Shor's algorithm, the Groover's algorithm, and recently, this work is actually inspired by some recent work. Two of the authors are actually here, and is basically saying that for solving d-dimensional linear equation systems, I guess you'll talk about it tomorrow in details, that you can find a speed up from a linear d to polylog d. So of course, this is assuming a weaker output requirement, which is a quantum state whose vector representation is roughly the solution to the linear equation system. And similarly, we assume such kind of weaker, I guess, output, and also an input model, which is a quantum oracle. So here is how it works. So this is, we call it quantum leading PCA. So we assume some input model, which is a quantum oracle, which generates a quantum state, whose vector representation is V0 and A. V0 is the initialization, and A is the covariance matrix. And later on, we're going to use something like UAS, UAE, but I'm not going to talk too much about this detail. And then again, it is going to assume an output model, which is a quantum state whose vector representation is Vk. Vk is the final output after you do k such iterations. Okay, so the main result is under a warm start. Of course, again, you want to make sure the initialization does have some component along this principal direction, and there is a quantum algorithm which prepares a quantum state with vector representation Vk, such that you have this precision. So it is basically very accurate with a precision epsilon and with probability at least 2/3. So this is using this many queries for these quantum oracles to the A, and order 1/phi queries to the initialization oracle.
You could get log 1/phi, right?
Yes, that's true.
So one thing, then you get worse, this. But you improve the dimension. Is that?
Yeah.
Actually, you can show that 1/phi is a lower quantum lower. If you want to
Yeah, I didn't talk in the slides, but there is a lower bound on 1/phi.
Oh, I see.
Yeah.
So question, is there a guarantee of success in the state preparation?
Oh, maybe Tong-Yang can comment on.
You can succeed with high success probability set with 2/3. You can just repeat, right?
And you know
But I guess your question is to preparing the states?
Is it heralded? Can you prove that you prepared the state?
Yeah, so which is, I guess the question is different. Can you prepare the state?
The result is that with success probability 2/3, you can prepare a state that within epsilon distance to the true linear vector. So are you asking like
Okay.
lack
I
of?
mean, but the projection, the preparation of a measurement which projects onto the largest eigenstate can be done.
It is not a projection. It is just a preparation that we prepare. We have a unitary that really prepares.
So you assume there is a quantum oracle that prepares the state you need, but the state you need are basically the state from A, which tells you the sparsity of the A, and some other quantities. Here is like a query to a quantum state of V0, which is the initialization.
Offline.
Okay, cool. Right, so the basic intuition for this speed up is this Chebyshev polynomials can be significantly accelerated in quantum computing. Like I said, this is inspired from a previous work in 2017 that you're going to hear more details about tomorrow morning. I'm not the expert here, so I don't want to comment too much on this, but this is a very good application to show that it's a successful application to show that quantum computing computation for linear algebraic problems can actually solve a wide class of machine learning problems, and I'm pretty excited about that. Yeah.
So the Chebyshev, what was the improvement due to Chebyshev? Like even classically. So
Yeah, even classically, you can see that here. This is a spectral gap square root, like from delta to square root delta.
Can you go back to the one? Then you keep the square root. Okay, I see.
Yeah.
So you want
You still use that, so you still have the square
if
root.
you don't want the square root of 1/f, then you could just do this kind of a to the k, implement that on the quantum computer, right? A to the k, right?
Right, but on top of that, you also use this quantum walk idea and the linear combination of unitaries, And then use these two ideas, you could achieve better speed up, which is basically from D to polylog D.
I see. So you want one reverse further, then you use the shift. Correct. Thank you.
Yeah. Okay, so just to, I guess to conclude, I talked a little bit about introduction of how a wide class of machine learning algorithm and supervised learning could be reduced to method moments. And we also talked about using spectral methods. You could solve a wide class of, density estimation problem using method moments. And specifically, I showed an example of latent directional allocation and how you can use data aggregations to find the model parameters. And in the end, all these problems reduce to a tensor decomposition problem, which you can find in the guaranteed online learning algorithm to solve it. And I talked a little bit about quantum algorithms for learning leading eigenvectors, but in general, I'm very interested to see how quantum algorithms can be applied to learning tensor decomposition. Because basically a lot of problems need to go beyond matrices, right? So that's it. Thank you.
Yeah, well, I have a couple of questions. But
Sure.
let's start with one. I mean, I think you mentioned that this depends on phi, and the overlap between the initial state and the final state.
Yeah, it's a yeah,
from
you're
the
right.
time Unless something collapses,
You're-
right?
Yeah, you're right.
But in the classical world, at least, sometimes
There
you
are-
have mechanisms for burning, right? In Markov Monte Carlo with burning procedures. Do you have an idea
Yeah,
how to do this in the context of machine learning? Let's put it this way.
I don't know how to do this in quantum world, but we know that in classic, machine or whatever algorithms that you can actually think about other ways, like use that to find rough approximations. But those are, again, I believe, like I said here, linear algebraic operations, right? You can think about all these operations as linear algebra. I do think there is a hope that you can speed them up as well, but we don't know exactly how
But
to
even if
do
you
that.
don't, these might be fast, right? The burnings.
Well, usually it takes exponential time.
Even in practice?
In practice, well, in theory, I don't know in practice. Yeah.
Any more questions?
Yeah. Sorry. I mean, I can also understand, this PCA is a feature extraction method, right?
Right.
And which prepares the principal actor,
Right.
but it's in a quantum state, as you point out. And now suppose you manage to invent some technique which generates the quantum state corresponding to the components of the tensor in your tensorial decomposition.
Okay.
I believe this is what you want to do.
Right.
Is it clear how we would use features of that? Because you can extract polynomial features of the quantum state.
Yeah.
Is it obvious how to use that?
Yeah,
for
usually,
inference later on?
exactly. Usually in this prediction. So although you wanted to learn model parameters, you're only doing that to do prediction, right?
I
So
see.
the
To skip
final,
the step.
exactly, the final result, the final outcome you need is the prediction result. And therefore you can use actually those quantum states to get those final prediction, which is, again, in the paper we talked a little bit about this. Yeah. All right.
Okay, so if none left, thank you for
Okay.
one more time.
Thanks.
I think we're meeting at 1:30.